Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and in this module we will be talking about the concepts, some problems in rigid body. So this is part 1 of the discussion, and the key concepts are going to be the discussion of the rigid body dynamics in Eulerian as well as Lagrangian frames. So these are quite complicated motions, and we will slowly and steadily look at the motion of these objects in different frames of reference, right? The so-called Eulerian as well as Lagrangian. Okay, so the topic of our discussion is problems in rigid bodies. Problems in rigid body dynamics. Rigid body dynamics. Okay, so the key concepts are the rigid body equations, both the Lagrangian and we will have both the Lagrangian and the Eulerian frames. So we have seen that the typical equations of motion are the motion of the center of mass as well as the motion around the center of mass, which is the rotational motion. So the rigid body equations for general motion are the translation of the center of mass, and the rotation about the center of mass g, the translation and the rotation. Okay, so the first example could be so these equations are m dv dt is equal to f, and the second equation is dlg dt is equal to kg, right? So these are my equations of motion. First is the translation, the other one is the rotation. Now recall that the angular momentum about the principal axis. So the angular momentum about the principal axis in 2D will be given by A times, so A and B are the principal moments of inertia. So A omega 1 E1 plus B omega 2 E2. And then I think this is quite redundant to write, but AB are the principal moments of inertia, and omega 1, omega 2, omega 3 are the angular momentum about the principal axis, right? So then we saw that the case of the dynamically symmetric objects. So dynamically symmetric objects. So we have the case of spherical symmetry. So this is the case which is the easiest to follow, the spherical symmetry, right? So easiest of the motion, where my Lg, the moment of inertia, will be simply A times omega, where A can be taken common, right? So here we have A is equal to B. So then, let's say in the general case, all moments are equal, the principal moments. So then if we expect that there are no moments or torques or forces, then the body is not experiencing any net torque, right? So if the body is moving with no force, then under uniform gravity, we have that kg is 0, or omega is equal to omega 0, right? So we have that the angular, in this case, the angular velocity is preserved and the motion is determined purely. So let me call this first equation as 1 and the second equation as 2. So in the first equation, the motion is preserved, and in the second equation, the motion is about the center of mass, which is the rotational. So this is, the motion is only determined by equation 1. Okay. So then let us look at an example, a real life example of these spherically symmetric moving objects, and try to determine the motion of these objects, right? So the case is snooker ball, right? So we have the case of a ball. We have the case of a ball where the ball is moving forward with, let's say, the moment of inertia g. Well, the center of mass of the ball is g, and it is moving with a velocity v, right? And typically when this snooker ball or the billiard ball, when it is pushed, so when there is an impulse to this ball, we don't expect the ball to rotate about a purely vertical axis. Typically the axis of rotation will be slightly slanted from the vertical, and we see that this is what we have. And then we have the point of impact of the ball with the floor will have a a reaction force, and we don't know the direction of the force, right? So we expect that. So what have we got? So what we have is, we have a ball of mass m. So ball of mass m and radius b, right? This is in, so this is radius is b here. So this is in contact with the horizontal table, and we consider the general motion, and we allow skidding. So we have taken the most general form of this motion of the ball, where skidding is allowed, which means that we cannot expect to have the rolling conditions at the point of contact C. So skidding is allowed, right? So which means there does not exist any special relation. Between v, which is the velocity of the center of mass, and omega, the angular velocity. Typically v by b is equal to omega if we had rolling conditions, that is coming from point C. Okay, so then the rough table, we have the reaction x is not vertical, right? So it is not vertical. So we expect that m, so the forces of motion are m times v dot is x minus mg k, and the second one is lg dot is minus b times k with x, right? So these are my equations of motion: the translational motion of the center of mass and the rotational motion about the axis passing through the center of mass. So we see that my k is the my minus k is the vertically downward direction, or k is the vertically upward direction, and x is the reaction force. So the force is the one which is creating this rotational motion, this reaction force. Okay, so then what we have is lg is a times omega, or now we expect, we eliminate x. So what we do is we eliminate x, or A omega dot is B times mv dot plus mgk, right? So this is my, so if we eliminate this reaction force from our two equations, let's say A and B, right, we see that our net equation of motion, this is a spherically symmetric object, so we have the principal moment being A. So we get this equation, and this is cross product with K, right? So K cross K, there won't be any weight contribution, and we see that this is also equal to mb v dot cross with K, right? So now we are going to integrate with respect to T. So suppose we integrate this equation with respect to T. With respect to T, we see that the following equation arises. So A omega plus mgk cross V is equal to C, right? So this is our conservation principle. Okay. So this is the total conservation of the angular momentum. So that is it. And we expect that if we take, in this equation, if we take a dot product with respect to the vertical axis. So let me call this as conservation principle 1. So if we take, so taking dot product with respect to omega of equation 1, we see that this is also equal to, so we get is omega dot with K is n, which is a constant, right? So again, from the conservation principle. So the conclusion of this discussion is that this vertical component of the angular velocity is constant, or we call this as the spin. So this is a constant spin of this object. So this is the constant spin of this system. Okay, so then we have the special case of rolling. Suppose when we have a special case of sliding, that is the rolling, that is there is no velocity at the contact point C. So then what happens? So taking case, so this is a special case of the rolling condition. So we have the velocity of the contact particle C, right? So C, where C is the velocity at the contact particle C is 0. Okay, so then we have V plus omega cross with minus BK. So this is coming from our conservation principle here, right? So C, well, this is again not conservation principle. So this is the contact condition. So velocity, the translational velocity plus the angular velocity times bk is 0. So this is my rolling condition here. So the rolling condition tells us that that V plus bk cross with omega is 0, or from here we have that, well, so using this relation 2 in 1, so using 2 in 1, we see that AK cross omega is K cross C minus MB K cross V, right? And we have that this is also equal to K cross C minus MB K dot V times K. Well, we are using the simple cross products, vector cross product, minus K dot K with V, right? And then we have this is K cross C plus MBV, right? So we have V. So here we know that V is, well, so this dot product is gone because V is perpendicular to K. So V is the center of mass velocity and K is the direction perpendicular to this motion. So we only get that this following relation. Okay, so then if let me call this as our relation number 3. So from relation 2 and 3, so from 2 and 3, what we see is that V plus mb square by A, V is equal to B by A, C cross K, right? And then to find out, okay, so what is now the value of omega from this discussion? So we see that the value of omega is 1 by B K cross V plus Nk, right? So this is constant. So this is constant of motion. Okay then. So that's the value of B. So so the conclusion is, what are the, so I think this ball example is over here. So there can be some conclusions which can be drawn through this set of discussions. One conclusion is, it turns out that the only rolling motions possible are straight lines with constant speed, straight lines with constant V and constant omega, and there is a presence of a vertical angular component which is the spin of the body, which is constant. So despite the presence of the vertical angular component, which is the spin, despite the presence of the spin, the vertical spin. Okay, so then let us now look at some specific cases again. So one specific case is the free motion with axial symmetry. So how about the case where Ig is A, C, right? So the first case is this following. So we have, for example, we have common spherically symmetric objects, fall under this category, free motion with axial symmetry, right? So these are more specific cases of this axial symmetry. So common spherically symmetric objects. And then we have also more complicated objects than spherically symmetric objects. So more complicated motion than spherically symmetric objects. So for example, spherically symmetric objects, for example, that the examples I have in mind is like gyroscope. This example of gyroscope will appear towards the last few modules. And another example could be that of a pencil. The pencil has a rotational symmetry about its length axis, and there is also the axial symmetry is missing depending on how the pencil is, if it's a sharpened pencil and blunt at the other end. So okay, so then we can consider this setup with no force and no torque. So we consider either no force or no uniform gravity. So no force or no uniform gravity. Okay, so we expect that kg and lg dot is 0, right? So this is when gx, so this is in the presence of the principal frame, right? So in the principal frame, so g x1 x2 x3 frame. Okay, so lg in this case is a omega 1 e1 plus a omega 2 e2 plus a plus c omega 3 e3, right? And we expect that in this case my object has, let us say, we denote, so the E3 axis has a different moment of inertia than E1 and E2 axis. So let us now separately call the E3 axis as our axis A1, so our axis A. So our axis A is along this E3 axis, right? So we will call this axis A now, A of t, right? So now, of course, the norm of this axis A is 1 because this is a unit vector. So then what have we got? So suppose we have, so what are we doing is that let us denote our E3 axis by A, our axis A, and then let A be the position vector of capital A, so relative to G. So A is the position vector of point A relative to G, and such that we have the norm of A is 1, so this is AG, right? And similarly we have A dot, the velocity of point A dot is A dot is omega cross A, right? So the angular velocity will depend on the angular velocity of the body, and this is omega cross A. And similarly, now if we were to find this quantity, so these are the various quantities we'll be requiring when we calculate the figure out the equation of motion of these objects, these axially symmetric objects. So A cross A dot is A cross omega cross A, right? And this is also equal to A dot with A omega minus A dot omega A, right? We see that this is also equal to 1. So we see that this is omega minus A dot omega A, right? So we have that omega is A cross A dot plus lambda. Well, we transfer this on the left hand side, so omega is this plus lambda times A bar, right? Where my lambda, this quantity lambda is A dot omega. Okay, so then what we have is, if we were to write down the angular momentum conservation, so what we have is Lg dot is ddt of A cross A dot, right, plus C lambda A, this is 0. So this is our angular momentum and equation. And then similarly, if we were to write if we were to expand this equation of motion, so this is A times A cross A double dot plus C times lambda dot A plus lambda A dot, right? And this is equal to 0. And then if we were to take the dot product of this equation with A itself, right? So let us try and take the dot product with, so let me call this relation as star. So what happens if we perform the operation A dot star? So what we see is A dot star is going to be, so A times A dot with A cross A dot, where again, so we have, this is a scalar triple product. We have A cross A dot. So this quantity will be 0 plus C times, well, C times lambda. Lambda is the spin component, so that is N, and times A dot A. And this is also equal to, is equal to the total angular momentum. So this is, so this was LG dot. So LG dot was 0. We have, if we integrate this quantity, so this is equal to L, right? So L is acting along a direction which is along A direction, right? So along A direction, and well, I need to draw the diagram of the object so that all these directions are fairly clear. So we have these following axes. So we have the axis K and the axis X3, right? And X3 is also our axis K of the object, right? So now when we integrated our angular momentum equation, this becomes L times A dot with K, A dot with K, and we see that this is also equal to, so we also see that this is C times N, which is a constant, so A dot A is 1. This is L of A dot K, and A dot K is is this right hand side is just a constant. So the conclusion of this discussion is, again, the spin of the system along the vertical axis is fixed, it's constant, conserved, right? So let me call this angle as alpha, and then my this quantity on the right hand side will become L times cos alpha, L times cos alpha, right? And so the conclusion is that for these spinning objects, the axis of symmetry, so what is the axis of symmetry? This is my axis of symmetry. Axis of symmetry. The axis of symmetry of this moving object, they make a constant angle alpha with the vertical, and then so in such a situation, this moving object is going to swipe a cone with constant angle alpha with respect to the vertical. So that is fairly intuitive, right? So the result is that if the axis of symmetry of the body makes a constant angle with K, and it swipes out a cone around the axis G comma K, right? So now if we take the cross product, if we now take the cross product of this equation, which equation? So let me call this equation as double star. I think my previous equation was star. So if we take a cross product of double star with A, let us now, let us quickly skip the steps of taking the cross product, and let us see what is the result by taking the cross product. So A cross double star, and we see that this is also equal to A times A dot A dot A minus A dot A dot, right? And this is also equal to plus 0. 0 means that we have cross with the dot, the triple product will be 0. And then this is also equal to L A cross K, right? So again, we simplify this. We have this A dot A is 1, and A, we have that A dot with A dot. So this is 0. Why? Because the velocity of this axis is perpendicular to the orientation of the axis, and all we get is that, again, my A dot is going to be L over A times well, A, L over A times K cross with A, right? So this was A cross K, so I have swiped the sign because of a minus sign here, so it becomes K cross A. So again, the story here is, well, this is A dot. So the result is that again the angular velocity about the axis of symmetry. The axis of symmetry means the k axis is going to be fixed, and so the motion is such that the body is rotating about the axis of symmetry, or we call this as a precessing motion, right? So this is the axis of symmetry, or this is the precessing motion, okay, around g comma k, precessing motion, okay, with angular speed L by A, with angular speed L by A. Okay then. So I think at this point I'm all out of time, and in the next module we'll continue this visualizing this motion of the spinning top. This is our eventual goal. The top has lot of complicated motion. The first motion we have seen is spinning around a symmetric axis, which is the motion observed on the surface of a cone. And then there are several other motions which are more subtle, which we will see in the next module. So thanks so far for listening.